In this video, we are going to do two more problems where simple harmonic motion is graphed. So in this first problem here, an oscillatory motion is represented by x equals 0.06 cosine 3 pi t minus pi over 2. We want to know what is the period of the motion, what is the amplitude, and then we want to express the motion in terms of the sine function. So remember, this is the general format for how oscillatory motion is graphed, and it looks very similar to the function that we have in our problem. Now, this A out in the front here stands for the amplitude, and notice we have a number out in the front. It is this 0.06. So part B of this problem, what is the amplitude, is really easy. It's just equal to 0.06, and the unit should be meters. Now part A, what is the period of the motion? Well, this right here, the 2 pi f is 2 pi times the frequency of the motion. And we've got a similar expression right here. So 2 pi ft equals 3 pi t. So if we can solve this expression for f, then we can take the inverse of that and get t. Because remember, period and frequency are inverses. So I'm going to go ahead and solve this for f. So first I see that the pi's cancel, the t's cancel. So 2f is equal to 3, which means f is equal to 3/2. And the period is the inverse of that, which is equal to 2/3, which is equal to, if you want to turn it into a decimal, 0.667 repeating. So the period is equal to 0.667 seconds. Okay, last part of the problem. We want to express the motion in terms of the sine function. Now let's think back to pre-calculus and trig. What do cosine and sine actually have to do with each other? Well, if you remember back from the unit circle and stuff like that, the sine function is the cosine function shifted to the right by 90 degrees, which remember in radians is pi over 2. Now this right here represents what we call the phase angle, and that's just how much the cosine function is shifted to the left or right, and a negative phase angle shifts the function to the right. So the way we want to write this expression in terms of the sine function is just get rid of the phase angle altogether, because this is just the sine function. And that's our answer to part C. Now, I think it's always worth it to check your answers if you're able. It's really easy to check your answers here because hopefully you have a graphing calculator. So what I would do is I would just graph the original function on our graphing calculator. You want to make sure you're in radian mode. And then we can make sure that this expression that we've written here graphs the same thing as the original expression, and that's just a really easy way to check your answer, and I think it gives a little bit of a better understanding of the sine and cosine functions. Okay, so that's our cosine function. That looks nice. So we've got our amplitude up here being at 0.06, and we've got a period of that 0.67 seconds. So remember, the period is how long it takes to return to its original position. So that would be like that there. And that looks to me like it is about 0.67 seconds. So now what we want to do is we want to see if the sine function makes that same graph. And there's not a new line here, so it looks to me like those sine and cosine graphs match perfectly, so we know that we have the correct answer there. Okay, this next problem here is a little bit different. we're going to get information from a graph rather than taking a function and getting information from that function or making a graph from information that we're given. So we've got a 0.5 kilogram block is set into oscillation when attached to a horizontal spring. The block is on a horizontal surface with negligible friction. A graph of the position x of the function of the object as a function of time is shown in the figure. We want to find the period of the motion, and we want to find the frequency, the angular frequency. We want to express the position of the object as a function of time. We want to find the spring constant, the maximum speed, and the maximum acceleration. We've got a whole bunch of stuff to do with this problem. So first, finding the period is super easy. So remember, the period is how long it takes to do one full oscillation, so the amount of time it takes to return to its original position. So the object starts here at 12 centimeters. It does one full oscillation. By the time it gets to 2 seconds, so our period is equal to 2 seconds. Then the frequency is just the inverse of the period. So that would be equal to 0.5 hertz. And then we want to find the angular frequency of the motion. So we want to take this information here. 2 pi over omega equals 1 over f, and we want to solve for omega. So I'm going to do what I did in another video and cross multiply. So it's going to be omega equals 2 pi f. So omega is just going to equal pi, or 3.14 radians per second. Now we want to express the position of the object as a function of time. So we want to use our general expression for position as a function of time for oscillatory motion. So remember, the thing out front is the amplitude, and we can get the amplitude right from this graph. So this 12 is the maximum position that the object gets to, and that's 12 centimeters. And I'm just going to leave this in centimeters for this problem. So it's going to be x equals 12, and then it's times the cosine of 2 pi ft. Remember, 2 pi f is omega, and my omega is equal to pi. So it's going to be times the cosine of pi t. And remember that we might need a phase angle in there, which isn't given to us in this formula, but we know that it's possible. And it looks to me like no phase angle is needed here, because the cosine function is for when the oscillation starts at its maximum amplitude. So this is just where the cosine function starts, so we don't need a phase angle to shift this function to the left or the right at all. And then part E, what is the spring constant of the spring? Well, we know the period of this oscillation, and we have an equation for the period of a mass on a spring. So we can say that, and we'll be solving this expression for K, and I think it's better to solve for your missing variable first and then plug in numbers. So I'm going to solve this expression for K. I'm first going to divide both sides by 2 pi. And then I'm going to square both sides. So remember, this 2 has to be distributed to this 2 here and this pi. So we're going to end up with ts squared over 4 pi squared equals m over k. And to continue solving for k, I will cross multiply. And then if I solve that for k, I'll get 4 pi squared m over the period squared. Now I can go ahead and plug in numbers. So the mass of that block was 0.5, and the period was 2. So if you plug all of that in correctly, you should get that it is equal to 4.93. Remember, that's the spring constant, where the units are newtons per meter, because it's how much force it takes to stretch the spring. Then we want to find the maximum speed of the object. So this is one of the equations that is not given to us on the formula sheet on the official AP exam. So it's something that you should memorize or have typed into your calculator. And the formula is that the max speed of an oscillating object is omega times A. So omega was equal to pi, and A is our amplitude, which is 12. And again, I'm just leaving it in centimeters. So it is going to be 37.7 centimeters per second. And then this last part of the problem was to get the maximum acceleration. And the formula for maximum acceleration is omega squared times A. So we'll do pi squared times 12, again, just leaving it in centimeters. And that's going to be 118.4 centimeters per second squared. So there's kind of a lot going on with the problem, but really the main formulas we needed were just these right here. The only formulas that we needed for extra were for Vmax and Amax, and hopefully you should have them typed into your calculator. So again, these are the only 4 formulas you need for your oscillatory motion. You should be able to derive anything you need from there.